Okay, let's go and get started today. Today we're going to talk about some synchronous serial transfer concepts and Lab 4. And this lecture won't take too long, so you should have time to work on either finishing up Lab 3 and then work on Lab 4, or just work on Lab 4. All right, so last time we did asynchronous. Today we're going to look at some synchronous, and we're going to do a little more with synchronous transfer going forward as well. But let's go and get started here. So the first thing here, let's review how asynchronous worked. So asynchronous, which is what we did last time and what you implemented for Lab 3, you basically, asynchronous means we have a start bit that gets transmitted that starts the timing on all of the other bits. In other words, the start bit goes out, we wait one period, bit 0 goes out, we wait one period, and so forth all the way through. Now this could be bit 0 goes out first all the way up to bit 7, or it could be bit 7 first all the way down to bit 0. It depends on the system. With asynchronous systems, they tend to start with the least significant bit first and work their way to most, but that's not always the case. And then at the end, we have our stop bit that gets put on the line, which returns it back to the idle state so that it's ready for the next start bit to come in. So the purpose of the start bit is to resync everything on the sender and receiver, so everything starts at the same point. The purpose of the stop bit, return the line back to idle to be ready for the next start bit to come in. Now on the receive side of things, as soon as we see the start bit, we delay one period and maybe a half a period or some little bit of extra to get us into the middle part of this, or the center part of the actual bit value that's being sent, whether that's high or low. And then from that point on, this delay here has to match the delay there, be very close to it, so that we are in the middle or close to the middle of the bit here. If this was mismatched, for example, if this was twice the delay that we had up here, then we'd be on the wrong bit. We would have missed a bit entirely. If this was too fast, like half of that delay, we would be on that point, and then for the bit 3, we'd be on bit 1, and then for bit 4 would be in the middle. And so notice that timing matters here. It's important. And let me fix this. For some reason, it moved the picture over the top of the text. So let me just fix that real quick. Right about maybe there. Okay. All right. So note that it is important that the timing on this for each bit period matches the timing here. Also notice it's a little bit important to have this slight delay that we have right here, so that we're not sampling on the transition period, we're sampling when this bit value is stable. All right, and no, stop. Oh my God. All right, so asynchronous, note, is a little bit of a misnomer, and that's because the transfer rates have to closely match. In other words, the delay period for sending has to closely match the delay period for receiving, or otherwise they'll get out of sync and we'll get garbage data, we'll get the wrong bit at the wrong time. Now, if they're not matched, then we have problems. Now, today we're going to look at synchronous transfer as opposed to asynchronous. So asynchronous, even though the word asynchronous means without respect to time, really in practice what asynchronous means, it just means we resynchronize with the start bit. We're using that, and then we only have to stay synchronized for the rest of the serial data unit throughout the message. And then the next start bit comes in for the next serial data unit, we resynchronize again. So we have to have the rates close, but not exactly perfect. And the reason for that, the start bit is resynchronizing. Now let's look at synchronous transfer. So synchronous or asynchronous systems, like the one we just looked at, they have no shared clock signal. Notice back over here at this diagram, there's no clock signal that's being looked at. It's just they've already agreed ahead of time that the data rate, the baud rate that I'm going to implement is, like, for example, in your lab, I don't know, 100 bits per second. So this is going to be 100th of a second here. And on the receiving end, it's also going to be 100th of a second there. And those have to be agreed upon ahead of time. But there is no shared clock signal. And ironically, that makes them sensitive to changes in timing during the transfer of the serial data unit. But they resynchronize every time, so they don't have to stay synchronized or close to synchronized for a very long span of time, only for a short span of time. Now, synchronous communication systems, they actually share a clock signal. And ironically, that makes them less sensitive to changes in timing because they're both looking at the same clock. So that clock might run fast, it might run slow, but since both the sender and receiver are looking at that same clock, then it becomes much less sensitive to variations in that clock. And really, there are some advantages to that. So in a synchronous system, the receiver and transmitter must both have access to that clock signal. Transmitter usually generates the clock. Not always the case. It could be an independent clock. It could be the receiver generates it. But in most systems, the transmitter is generating the clock signal as it's putting the data bits out on the line. And that clock, how do they both share that? Well, generally, the clock signal has its own separate channel. Or there are some techniques that we'll see in a future lecture where we can actually combine the data with the clock and put them on a single channel together. And we'll look at that here, not this lecture, but a coming lecture, so later this semester. All right, so here's the basic idea with synchronous serial communication. We still have a source, we still have a transmitter, just like we had before, but now notice over here in the diagram I have two channels. I've got a clock channel, and I have a data channel, and noise can still affect both of these. So the noise could affect the clock, and the noise could affect the data. But on the receiver, it's looking at both the clock and the data, and it's using the clock to know when to look at the data here. So notice that the transmitter might be generating the clock. Notice the receiver might be looking at the clock, but they're sharing that. They're both using the same clock signal to know when do I put stuff on the line, when do I pull stuff off the line. And then from the source and destination point of view, it's really not any different than asynchronous because it's up to the transmitter to encode the data using this, the receiver to decode it. So you might still feed in, I don't know, the letter A. The letter A will still pop out over here. But with synchronous communication, it's using this clock that both the transmitter and receiver are looking at. So synchronous has that extra clock signal. It's used to synchronize a transfer. There's no need for additional framing bits because of that. So we don't need a start bit anymore. We don't need a stop bit anymore, as we'll see in a second. Asynchronous is a single channel with additional framing bits used to resynchronize. So the start bit to resynchronize, stop bit to return to idle. And notice that adds a little bit more overhead for asynchronous because we have that extra period. If we go back to here, we have this extra period of time where the line isn't sending data. It's sending the framing bits. Start bit, stop bit. Those are needed in order for that to work. So we have a little bit of extra overhead time with adding things onto the line that aren't part of the data. Okay, now, so synchronous systems generally use that separate channel for the clock signal, just like we had in this diagram back here. Some synchronous systems will use self-clocking data streams, like I said, that encode both the clock and the data on a single channel. And like I said, we'll look at that more in a future lecture. But either way, synchronous systems have a clock signal that's shared between the transmitter and receiver. Whether it's encoded on the channel with the data or it has its own completely separate channel that's independent from the data, it's for it to be synchronous, they both have to have access to that same shared clock signal. All right, now let's look at an example of a system that uses a separate clock channel for right now. All right, so here's what that system would look like. So notice here, we've got the two channels like we saw before. We have a clock channel and we have a data channel. And the clock channel, in this case, basically just is going to go low for a period and then high for a period and low for a period and high for a period. So think about that as the clock ticking. So like tick, tock. That's one cycle of the clock. And then the next cycle, tick, tock. Next cycle, tick, tock. And we repeat that for all 8 bits. Notice on the data channel here, there is no start bit period. There is no stop bit period. Notice it's just all data. So for each complete tick of the clock or clock cycle that happens, we have 1 bit worth of data. So in other words, the clock ticks for each bit of data. I mean, it ticks and tocks, goes low, goes high. And the data line is changed on the first edge of a clock cycle, meaning the data, when this goes low, that's when the transmitter puts the data on the line. You can see that represented. Every time this is dropping low, in other words, these transitions without the arrow going up, maybe I should have drawn an arrow going down there, but without the arrow going up the falling edge, that's when the transmitter is putting the data on the line. And then the receiver, when it sees the clock line go high, that rising edge, everywhere we have that arrow, that's where it looks at the line. So notice that that puts us right in the middle of that data bit. So we put this low, put the data on the clock channel, the line ticks high. We then read the line on the receiver. So the data line is changed on the first edge of each clock cycle, in this case the falling edge with the clock idling high like we have, and then the data line is read by the receiver on the second edge of the clock when it goes high. Now there are systems that read on both the falling edge and the rising edge. For example, some memory that's in your PC transmits data synchronously using a clock to talk to the memory SIM cards. And those are like the DDR RAM modules. DDR is dual data rate. They do something like that where the clock goes low, it transmits data, clock goes high, transfers data, and so forth. But in most systems, it's like this. Data is what's called set up or put on the line on the falling edge for the first clock cycle edge, and then it's sampled or read on the rising edge. Now, the clock polarity and bit order might vary for different systems. For example, the clock polarity, the clock idles high, meaning the falling edge is when setup happens, the rising edge is when sample happens. But if the clock idled low, then it would set up on rising edge, sample on falling edge. It would just look inverted from the way we have it now. And then the bit order we have here is most significant to least significant. That could be inverted as well. It could be D0 here, D7 there. But I will say this, that while most asynchronous systems go least significant bit to most synchronous systems go from most significant bit down to least. And there is an advantage to going most to down to least in that if you were to look at this on an oscilloscope, it would read out right to left the way you would write it down on a piece of paper, where most asynchronous systems are backwards from that. So just keep that in mind if you ever are looking at those. Now, let's look at the letter A being sent on a synchronous system. So the letter A, 8-bit byte, which is the decimal value 65, so this is capital A is a 65, it might look like this. So in other words, 65, if you think of what that is, in binary, that's a 1 in the 64's place, and a 1 down here. So 64 plus 1 is 65, so all zeros except for 1 and 1, and you can see that here in the data. And then here's the clock ticking. So what's going to happen is the clock goes low, the transmitter puts the 0 on the line for the most significant bit, and it leaves that on there until the clock goes low and it puts the next bit on. But it goes low, halfway through, ticks high, goes low, ticks high. So low, 0, high, that going high, the receiver reads the 0. Goes low, puts the 1 on the line. Then when this goes high, the receiver reads the 1. So it's read 0, 1, and that process continues. The next time the receiver sees this rising edge, reads a 0, reads a 0, reads a 0. So this is it sampling the line. Sample the line, get a 0. Sample the line, getting a 0. Sample the line at the end, get a 1, and then goes back to idle. And again, notice there's no period here where we need to have a start bit. There's no period where we have to have a stop bit. And the line doesn't even necessarily have to idle high here. It could have, if this ended on a 0 bit, the line could have stayed low, and that would be fine. Because there is no, it doesn't matter if the data line idles high or low. It's just because the only time that the receiver ever samples the line is when we see this clock edge rising, in this case. So the clock is what is keeping everything synchronized, and since the receiver can see that, it knows exactly when to sample the line. And that's one of the reasons why synchronous serial communication is actually less sensitive to timing. We could stretch this period out for as long as we wanted to, or make them shorter if the lines will handle that. And so we could run this at different rates on the sending end and the receiving end. And the other end would be fun because all it cares about is when does that rise. So it's kind of a little bit ironic that synchronous systems are less sensitive to variations in timing. Asynchronous systems have to have an agreed upon baud rate on the two ends in order for them to work right. So notice the advantage here, less sensitivity to timing because we're sharing that clock. The other advantage of this system here, no overhead for a start bit period or stop bit period. And also notice though the disadvantage, we need a separate channel to put this clock on. Okay, so here's the kind of sequence that you would have for a synchronous communication. So the transmit sequence, notice we set the clock line low, and at the same time we place the bit on the data line. So the data bit goes on the line and this is the transmitter is generating the clock signal. So that goes low, we put the bit on the data line. We delay for 1/2 clock period. We set the clock high, delay for another 1/2 clock period. And then we're going to repeat that for all of the bits that we want to sense. For all 8 bits of our byte, we're going to do that. So we'd have this inside of like a for loop that goes through for each bit in our byte that we're sending. If it's an 8-bit byte, we're going to do this 8 times. We'll have a for loop run that says, set the clock low and low, put the bit on the line, delay for a 1/2 clock period, set it high, delay for a 1/2 clock period, and then repeat that. So we're going to basically go through for all 8 bits like we see here. Now on the receiver, notice how simple this is. It's wait for the clock to go low, and then sit and wait again for the clock to go high. And as soon as that clock goes high, we read the bit by sampling the line and say, okay, the clock went high, read the line, there's a 0 on the line. Store that in our byte, and then we would count up. As soon as we repeated this 8 times, we would have our entire byte. 0, 1, 0, 0, 0, 0, 0, 1. We have 8 of those now printed out. There's our capital A coming out. So notice this is a little bit simpler than because we don't have, notice there's nothing in here about on the receiving side about having to delay or waiting or anything for a certain amount of time. All we're doing is looking at the state of line. So while this would be like a while loop. While it's high, wait. While it's low, wait. And as soon as we are done in that while loop there, just read the line. Stick it on the byte, build that up just the same way we did with asynchronous. And as soon as I get 8 of those, print it out, clear it out, and go back to waiting for the clock to go low again. So very, very cool. But again, we have this added complexity of the extra clock line. All right, so again, each bit's placed on the line when the clock goes low. And the receiver is just waiting for the rising edge of the clock signal. It's just waiting for the clock to go high. As soon as the clock goes from low to high, we read the bit and then wait for the next bit. Very simple. It's a pretty cool concept. Now, one thing that I mentioned earlier that I'm going to mention again is if the clock polarity were reversed, we would basically just set up the data on the rising edge and sample the data on the falling edge rather than vice versa. But the concept is the same. So different systems might have different clock polarities specified, but all that matters is both the sender and receiver agree on what the clock polarity is. When do I sample? When do you set up the data? And if it's the clock polarity is reversed, you just switch highs and lows around. And notice this code that we had back here, this pseudocode, would be the same. The only thing would be set the clock line high, delay for our 1/2 period, set the clock line low. And this would just be wait while it's high, or wait for it to go high, wait for it to go low. And so we just reverse the lows and highs in here. It's the same concept, works exactly the same way. Okay, now some real-world synchronous systems that are out there that are used. You probably actually used synchronous serial communication of some sort. Actually, I can guarantee that you use something like that today. For example, if you used your laptop, moved your touchpad on that, you use that. If you logged into a Zoom call, you probably use that. If you some sort of synchronous method. If you use your smartphone, I guarantee you used synchronous communication system. So SPI is kind of a standard. It's also kind of the same. Microwire is a brand name of SPI. And we're going to look at these more carefully later. But I2C is also a way that chips and devices talk to each other. And inside of that, I2S is like an version of I2C, but deals with sound. So when you're talking on your cell phone, or you're listening to a voicemail, or even if you're playing a sound and there's audio coming out of this, that's coming through an I2S, most likely coming through an I2S data stream that's sending that sound data out to the speakers, or receiving the sound from the microphone on the smartphone, getting it into a digital form. So these are all used inside of system designs. Your laptop has SPI devices, I2C devices for temperature sensors, I2S devices for sound. So these kinds of things are all in there. Also, if you have a desktop PC and it has a PS2 port on the back, PS2 is a type of synchronous communication mechanism. The keyboard port on a PC actually has a clock signal. When you press a key on the keyboard, it puts ticks the clock signal, marches the bits out that go with the scan code for that key, and that's how the keyboard is designed, and that's how the PC knows what key was pressed, is it's all done with that synchronous system with that clock signal. Same thing if you have a PS2 mouse. Most people don't have. Most keyboards and mice are now USB, but a lot of desktop systems still have a PS2 port on them. Also HDMI. If you connected your television and or your monitor for your PC by HDMI, I have a second monitor here set up that's connected over HDMI. That's a synchronous communication system. There's a clock in there. But in order to reduce the clock frequency, they actually send 10 bits for every clock cycle. 5 for when it goes low, 5 for when it goes high. And so it's kind of a hybrid of synchronous and asynchronous. There's a clock, but there's a little asynchronous period where it samples the line multiple times. And those 10 bits are sent for there's 10 bits sent for red, for green, for blue, for every pixel worth of data that goes across there. Also DVI, which is like the older style monitor connection. Not VGA. VGA uses analog signals, but DVI, digital video interface, that also has a clock signal that's used for each pixel. So this stuff is real stuff. It's really used and stuff. Now, what we're going to do is you're going to work on Lab 4, and you're going to transfer data using synchronous communication. So what I would do is start with your previous lab, because that's already set up to kind of divide get the key, divide it up into the 8 bits, send it, receive the 8 bits, put it back together, but you're going to change how it actually does that, dividing up and putting back together. And in order to do that, what you're going to need to do is, because we're going to have an extra clock channel, you're going to need 2 wires instead of 1 connecting the Arduino boards. So 1 wire for the data channel, another wire for the clock channel. So last time you only needed just 1 data line, now you're going to add a clock channel. So I would set up your lab from last class, do a save as on it for the sender, save as on the receiver, change the name of it for lab 4, send, lab 4 receive, so you don't accidentally overwrite your lab 3. And then add that extra wire, figure out what pin you want to use, and then modify the code so it works with synchronous rather than asynchronous. And as a guide for how to do that, you probably want to look at this slide back here, this slide 10. But let's go ahead and look at the lab assignment sheet and take a quick look at that, and then I'll give you time to work on that today. So, all right, so here's what the lab sheet looks like. So notice it says for this lab, you're going to connect 2 Arduino boards with simple wires, get them to communicate simple information using a synchronous communication method. You can work with a partner if you have a roommate or somebody in your social group, or you can work by yourself. Doesn't really matter. If you do work with a partner, though, make sure in your comments for your code, make sure to put who you worked with on that. And essentially, you're going to write 2 Arduino programs just like last time. A sender and a receiver, and essentially here's the detail for how that's going to work. So you're going to have 2 I/O ports instead of 1 that's going to be the data channel, one that's going to be the clock channel. You're also still going to use the LED so you can see it blink as the stuff goes over, but you've already set that up. And in the loop here, you're going to read a key from the serial interface, send all 8 bits of the character 1 bit at a time, using or toggling the clock signal and delaying for each high-low part of the clock pulses described in the lecture that we just saw in that slide we were just on. Now, I would set your data rate for 10 bits per second. Now, 10 bits per second, that means your clock period, remember from that slide 10 in the lecture, it's half of that. So instead of at 10 bits per second, rather than delaying for 1/10 of a second, you're going to delay for half of that, or 1/20th of a second for when it's low, and 1/20th of a second for when it's high. And the same thing for each of the corresponding bit periods, because there's a low part of the clock and a high part of the clock for every single bit worth of data. Now on the receiver, it's basically going to do the same thing. You're going to wait for the clock pin to go low, and then you're going to wait again for the clock to go back high. When it does, you're going to read all 8 bits by waiting for, and actually this should probably say rising edge there. I'll fix that. So you'll sample a line on the rising edge, set it on the falling edge, and then I want you to demonstrate that system working at 10 bits per second, 1,000 bits per second. And then I want to see how fast can you get it to go? How small a delay can you get out of that? What's the shortest amount of time you can get for that delay? Or could you even take the delay out entirely and get it to work? But I want you to tell me in your when you submit that, you can put it in the comments at the top or whatever. Tell me what the fastest rate you could get out of it would be. Okay, let's go back to the lecture for a second and finish things up here. All right, so finishing this up, where we are right now is we looked at the lab sheet, and again, you're going to want to implement that something like this. Refer back to this when you go to write that code. And that's all for today. So finish up your lab 3, work on lab 4. Make sure to stay safe, wash your hands, wear a mask if you're out and about, and around people not from your immediate household. But if you have any questions or problems, let me know. One quick note here. I know a couple people had mentioned that they're having problems getting Arduino to work with 2 instances of it running on one laptop. And there is a trick to get that to work right. The trick is to open Arduino through, here, let me show you real quick. Let me switch over to the display. All right, actually you can't see that because it's off the bottom of the screen here. But anyway, if you bring up this and go to Arduino here, that says Arduino, you'll launch one of those. So here you'll would write your code into this window. And one of the things that I noticed, the people that had problems, and I had this problem as well, is if you go up to here and say File, Open, and open another one, it'll bring up another window and it'll look kind of like this. So where you go up to Tools and you set this to what port you want it to be and what processor you want it to be, what you'll need to do is rather than launching and opening another window through here, open it through the Start menu again to get another instance. So click on Arduino again. You'll have another separate instance. And then now you have 2 windows, and the serial monitors will be separate for each of them. But you'll have to come into here and say Tools and set this to the other port. So set this one to one port, set this one to the other port, and then that should work. And the people that were having that problem, that worked for them, that worked for me as well. So just make sure you open it that way. All right, so that's it. Work on your labs. Relatively short lecture today, about a half hour worth of lecture. Rest of the time now you have, an hour and 45 minutes worth of time to work on your labs, get those done. Again, if you're having trouble and you're struggling, send me a text message, send me an email, call me on the phone. If I don't answer, leave a voicemail. I'm here to help. And if we need to, I can set up a Zoom meeting really quickly. And you can show me your code, you can share your screen, and we can work on stuff together. But you got to let me know if you're struggling. All right, that's it. Stay safe.